The second law of thermodynamics. Many thermal processes proceed naturally in one direction but not the opposite. These processes are called irreversible. For example, heat by itself always flows from a hot object to a cooler object, never the reverse. Although the reverse process would not violate the first law of thermodynamics, energy would be conserved. In order to properly account for irreversible processes, the second law of thermodynamics was formulated. Sadi Carnot is credited with having formulated the second law of thermodynamics in 1824. Heat flows naturally from a hot object to a cold object. Heat never flows spontaneously from a cold object to a hot object. When you place a warm cube of iron next to a cool cube of iron, heat flows from the warm cube to the cool cube until they reach an equilibrium temperature. Heat does not flow from the cool cube to the warm cube. This would make the cool cube even colder and the warm cube even hotter. This would violate the rules of nature. Kinetic energy of macroscopic objects, like a ball or a pendulum, is associated with organized, coordinated motions of many molecules. In contrast, heat transfer involves changes in energy of random, disordered molecular motion. Therefore, conversion of mechanical energy into heat involves an increase of randomness or disorder. The energy is conserved, it's just no longer usable to do work in the system. Entropy provides a quantitative measure of this disorder. The symbol for entropy is capital S, and its units are joules per Kelvin. The total entropy of an isolated system never decreases. The mixing of these two liquids cannot be undone. Entropy increased by mixing, and it can't be reduced. An important statement of the second law of thermodynamics. The entropy of an isolated system may increase, but can never decrease. When a system interacts with its surroundings, the total entropy change of system and surroundings can never decrease. When the interaction involves only reversible processes, the total entropy is constant. And when there is any irreversible process, the total entropy increases. A heat engine is a thermodynamic system that converts heat into mechanical energy, which can then be used to do mechanical work. Denis Papin, around 1690, was the inventor of the pressure cooker, and he first described three basic components of any heat engine: a high-temperature reservoir, a low-temperature reservoir, and an engine containing gas or steam. Here's how a heat engine works. The hot reservoir is at a high temperature, and it transfers an amount of heat, Q sub H, Q high, to the engine. In the engine, part of the heat is transformed into work. That's during the expansion of the gas. The rest of the heat, Q sub L or Q low, is exhausted to the cold reservoir. The efficiency of a heat engine depends on the heat transfer between the reservoirs and the engine. The efficiency equals Q high minus Q cold over Q high. One of the important challenges in engine design was that of increasing efficiency. This question was answered in 1824 by the French engineer Sadi Carnot. Carnot proposed an idealized heat engine, the Carnot engine, that would provide the maximum possible efficiency consistent with the second law of thermodynamics. The Carnot engine operates between a high-temperature reservoir at T sub H and a low-temperature reservoir at T sub L. The Carnot engine consists of two reversible isothermal processes from A to B and from C to D, and two reversible adiabatic processes from B to C and from D to A. No heat engine operating between two temperatures, T high and T low, can have a greater efficiency than a Carnot engine operating between the same two temperatures. The ideal efficiency is temp high minus temp low divided by temp high.
The efficiency is also written as work over the high heat. Note, these temperatures are in Kelvin, and this equation is not on the AP Physics 2 equation sheet.